Hello, welcome to this video. I'll try in this video to explain how to find the distance from an arbitrary point in space to an infinite linear charge of arbitrary orientation. So in class we have seen that if you have a linear charge, an infinite linear charge, like the one shown here, okay, so this is a linear charge, this along the z-axis. It has a linear charge density of rho L coulomb per meter. Then at any point in space, what we have to do in order to calculate the electric field is to find the normal distance to this linear charge. We call this one rho, and to find this unit vector pointing outward, which is going to be a rho. If this is z-axis, this is going to be a rho, okay? So then the electric field is simply given by E equal to rho L over divided by 2 pi epsilon naught rho a rho. So in order to be able to calculate this expression, I need three things. The value of the linear charge density, which is given the problem, the normal distance from the observation point where I'm measuring the field to the linear charge. So this angle here is 90 degrees, and the unit vector a rho. This is okay if we have a line charge or linear charge oriented along the z-axis. But what if we have a general line in a three-dimensional space? How do we calculate this distance rho, and how to calculate this unit vector a rho? So let's see how we can do that in the general case. Okay, first let's talk about a general line. A general line can be given by a parametric expression, and this parametric expression requires two things. One point on the line, which I'm going to call here R1, and the direction of the line, which I'm going to call S. If I know with just one point, any point along the line and the direction of the line S, then any point along the line can be written in this form. R is equal to R1 plus TS, and T is a parameter. Okay, for example, let's take a look here. If I pick, say, this point here along the line, okay, then this is the origin here. I'm gonna try to find the position vector of this point. So this point here, this one here is the origin, okay. So I'm gonna call this point here R. This is called R, okay. So you can see that R is a vector. It can be written as the sum of R1 plus this part here, and this part here is another vector which is equal to t in the direction of s. So I moved a distance t in the direction of s. Okay, so here, as you can see from this figure, that any point along the line can be written as r1 plus ts, and of course if I make t equal to 0, I have the point r1. If I make t very large, then I'm moving along that line. So every point along the line corresponds to a specific value of t. So this is called the parametric equation of the line. Okay. Now our target is, if you are given this parametric equation, you are given r1 and you are given s. How can you find the normal distance from any point in space to that line? This is really the target that we'd like to solve, because this is what we're going to need in order to calculate the electric field resulting from an infinite linear charge with arbitrary orientation. Okay, so this is the problem we'd like to solve. We have a point called R2 here. Okay, it's a general point in space. We have our line, and we know a point of the line called R1. We know the direction of the line called S. My target is to find this normal distance rho and to find this unit vector a rho, which is pointing normal from the line to the observation point R2. Okay, the strategy, one possible strategy of doing this, and there may be some other ways of doing it, is to do the following, and this is what I'm going to be doing in this video. First, find the vector R12. So the vector pointing from first point on the line R1 to the observation point 2 here. And then we'll try to decompose this vector into two parts: a tangential component along the line and a normal component to the line. Okay, and we did mention something like this before in class. So this vector here, this red vector, this is called R12 tangential. It's called tangential because it is in the same direction as S, as the direction of the line. And this other vector here, which is normal to it, is called R1, 2 normal. Okay, so my target is to use projection to get R1, 2 normal, because once I have R1, 2 normal, I know what is rho, because rho is the length of this vector, and I know what's a rho, because a rho is simply equal to this vector divided by its length. So this is really how my strategy will go in solving this problem. So this is a projection problem. I will try to project this vector, which is R1, 2, along the direction of S. How did we do that in class? First, we found a unit vector in the direction of S, and then we projected R1, 2 in this direction to get the length L. We call this length here L. So I'm just gonna illustrate this one here. So we call this length here L, okay, by doing a dot product. And once I have L, I multiply it by a unit vector along S to get R1, 2 tangential. Once I have R1, 2 tangential and I have R1, 2, I'm able to get R1, 2 normal, because R1, 2 normal is equal to R1, 2 minus R1, 2 tangential. So let's see how these steps are going to be done in the next slide. Okay, so these are the steps we're going to do. First, we connect any point along the line. Really does not have to be R1 to the point R2. I selected R1 just for simplicity, so I found the vector R1, 2. So R1, 2 is R2 minus R1, okay? Then you find the unit vector along the direction of S. Unit vector along the direction of the line is the vector S divided by its norm. Now we do a projection, a scalar projection of R1, 2 along S. So you take the dot product between R1, 2 and AS, okay? And this is what we do here. If you do that, this gives you this length L. Remember, dot product, when you do a dot product between a vector and a unit vector, you are getting the length of the first vector along the direction of that unit vector. So the projection of the length, the length of the projection. So if you project R1, 2 in the direction of S, this is the length L you are going to be getting, and it's given by this expression. This is a very simple application of inner product or dot product. Now, once I found the length L, I know this vector here, which I called R1, 2 tangential. R1, 2 tangential is equal to L multiplying AS. So once I found R1, 2 tangential, I can get R1, 2 normal, because R1, 2 normal is equal to R1, 2 minus R1, 2 tangential. Once I have R1, 2 normal, I know what is rho. So this length here, which I call rho, is the length of this vector, okay? And A rho, which is the unit vector in this direction, is simply equal to the unit vector in direction of R1 normal, which is simply equal to R1 normal divided by its length. So this is really the procedure for calculating this distance. Let's see an example of how we can do that with numbers. Okay, we have here a problem. The line is given by a point on the line R1 has position vector 3, 4, and 5. And the direction of the line S is given by the vector minus 1, 1, and 2. And we would like to calculate the field at the point R2, which is 5, 3, and 2. So in order to calculate the field at R2, I need to find the normal distance. So I need to draw this normal distance here, okay? And to find this unit vector. So I need a rho and I need this rho. So the way of doing it, as we said, as explained before, we're going to connect R1 and R2 to get the vector R1, 2. And then we are going to decompose this vector into two components. This vector here will be called R1, 2 tangential. And this one here, the normal one, is called R1, 2 normal. Okay? So this is what you see is happening here. So I first wrote the expression actually of the line here. So the expression of any point along the line is equal to R1 plus TS. This is R1 and this S, so it's going to be 3 minus T, 4 plus T, 5 plus 2t. This is the expression for any point along the line. If you give t any value, you obtain any point along the line. So any point is really corresponds to some specific value of t. Okay, so we proceed. We first calculate r12. So this vector r12 is equal to r2 minus r1 as we explained in class. I notice the change in order. So this is r2, this is where I'm observing my field, and this one point along the line. 5 minus 3, 3 minus 4, 2 minus 5. You get this vector here, which is r12. In order to do the scalar projection, you need a unit vector along the direction of s. So I calculated AS is equal to S divided by norm S. This is S that's given. The norm of S is simply the square root of minus 1 squared plus 1 squared plus 2 squared, so square root of 6. So this is the unit vector here, okay? So the length L, which is this length here, is nothing but dot product between R12 and AS. So I do this inner product. So 2 multiplying minus 1, you get minus 2. Minus 1 multiplying 1, you get minus 1. 3 multiplying 2, you get minus 6. So this gives you minus 9 divided by square root of 6. So I did dot product between this one and this one. Okay? So we found that the length L is minus 9 over square root of 6. Someone may ask me, how can the length be negative? Well, as I explained in class, when the length is negative, this does not mean that we have a negative length. It actually means that the angle between R12 and AS is more than 90 degrees. So the situation really that we have is a little bit different from the one I'm drawing. It looks something like this. Okay, so this is R12 and this is AS. Okay, so the length we calculated is really this length here. So the length is correct, and we have to include that sign. Okay, because this sign is simply saying in order to do the projection, you have to move against S, not with S. So this part here is really the vector projection of R12 along S. You can see it reverses the direction, so I have to keep the negative sign. I cannot remove the negative sign. Okay, once I found L, which is this length, I can get this vector, which is R12 tangential. R12 tangential is nothing but a length L along AS. And I have to keep the sign as explained earlier. So this is L and this is AS. You multiply them, nice. Square root of 6 by square root is going to give us 6. 9 over 6 give us 3 over 2. Minus 9 over 6 give us minus 3 over 2. And minus 9 multiplying 2, which is minus 18, divided by 6 will give us minus 3. Okay, so we found that vector. What remains is to find R12 normal. Okay, so R12 normal is equal to R12, which we already have, minus R12 tangential, which we just calculated. So this is R12, this is R12 tangential. Okay, so let me see here. Did I make a mistake in this calculation? Yeah, I made a mistake. Well, it's not a mistake really, I mistyped it. So this is minus 3 here, okay? So this one is minus 3. Okay, so that's fine. So minus 3 minus minus 3 is going to be 0. 2 minus 3 over 2 will give us 1/2. Minus 1 plus 3 over 2 is going to give us 1/2. So R12 normal is 1/2, 1/2, and 0. Is this answer correct or wrong? Well, if this is indeed normal to S, then when you take the dot product between R12 normal and the S, you should get 0. And indeed, if you take the dot product between this one and AS, you get 1/2 minus 1 plus 1/2 multiplying 1, you get 0. And this is 0 multiplying 2 doesn't contribute, okay? So indeed, the inner product between AS and this vector is 0. So now we know what is rho, because rho is nothing but the length of this vector. So the length of this vector is the square root of 1/2 squared plus 1/2 squared. So it is square root of 1/4 plus 1/4, square root of 1/2. So it's 1 over square root of 2. So this length here is 1 over square root of this, what we call rho. Now, I want to get a rho. A rho is a unit vector along this direction, okay? So a rho is nothing but this vector divided by its length, which is rho. So if we divide this vector here by 1 over square root 2, this is equivalent to multiplying by square root of 2. So this becomes 1 over square root 2, and this becomes 1 over square root 2. So I divided this vector by its length, and this will be the arrow I got. Now you are ready to, if you are given the linear charge density, to calculate the direction of the electric field. The electric field will be pointing in this direction at the given observation point R2.